one singular.
All right.
Actually, I have like a rotation of four.
So just like matrices, and just like the dot product, we have to look at the properties. Math is getting complicated because sometimes the order matters and sometimes it doesn't. With matrices, it matters which order you multiply. Dot product doesn't. Cross product, it does as well. U cross V is not the same as V cross U, but they are very similar. They're almost identical, they're just opposite vectors. They just go in the opposite direction. So U cross V is going to be perpendicular to both U and V. One of them is going to go up, V cross U would go down. Think of your right-hand rule, your thumb will either point up or your thumb would point down, depending on which vector your index finger is pointing to. You can distribute. But I don't know why you would, there's not very many times you would want to, but you can. Because it's much easier to add vectors first and then do the cross product than it would be to do the cross product twice. Because remember the best, well, probably the easiest way to remember the cross product was that determinant method that we were using the other day. If the cross product is 0, this is a new way to show that vectors are parallel, as long as one of them is not the 0 vector. If you have the 0 vector and you multiply dot product or cross product, you're going to get 0. So, if the cross product is 0, then they're parallel. Also, if they're parallel, then the cross product is 0. Now that might sound like it's the same thing twice, but in mathematics, same things in order matters, right? Because I can say, here's a classic example of where order matters. All horses have 4 legs. That's a true statement. But if you switch it, well, we're not talking about accidents or, those crazy 6-legged horses. But if we switch it, not all 4-legged things are horses. So one direction does not necessarily imply the other direction. However, in this case, it does. So if they're parallel, the cross product is 0. If the cross product is 0 and there's not a 0 vector, then they're parallel. So they're not completely the same. We have to have that one restriction that you don't have a 0 vector in there. And if you have, and does yours have a typo here without an X? So that should be a cross product. If you have a constant out in front, you can put the constant in either one of the vectors first before you do the cross product, or you can do it afterwards. So these are the properties of the cross product. Most of them seem intuitive, but as you learn more and more complicated math systems, we start to have certain things are allowed in some systems and certain things aren't allowed in other systems. So, consider these vectors. We want to use the cross product to show that the vectors are parallel. So again, for the cross product, for this first part, I would ignore those, and I did the determinant to get -4 minus -4. For the second one, I ignored those ones, and I did the determinant, plus I put a negative out in front, because the second one is always the negative determinant. And finally, for the 12 minus 12, I cross out those ones, and I would find the determinant of the matrix that's left. Of course, if you didn't learn matrices first, I couldn't really teach you this shortcut. I could make it up, I guess, but it's much easier that we've thought of matrices and can connect those two ideas. Okay, so we can use the cross product to show that they're parallel, and just a reminder, just a little bit of review, you can also show two vectors are parallel by showing that one is a scale multiple of the other. So you could multiply vector A by -2, and then it would perfectly match up with vector B. So that would be another way to show that they're parallel. So on your test, if I ask you, are these vectors parallel? Now you have options. You're going to have lots of options for parallel and perpendicular. So that might be one of the things you start to study is, what are all the ways that I can show something's parallel? What are all the ways that I can show vectors are orthogonal or perpendicular? And our last main application of the cross product is to physics and to torque. So you probably had a torque formula in physics, and the torque formula is just the cross product of the force applied and the force or the vector coming off of the object that you're applying force to. So torque is just A cross F, which is the length of A times the length of F times sine of theta. And this formula you would have had in physics without knowing that it was just the cross product that was being applied. So the vector A is the arm, the vector F is the force acting on the arm, and the units for torque are Newton meters because your force is in newtons, and whatever arm you're using is measured in meters. So here is a question. You have a wrench, 15 centimeters long, used to be tightening a bolt. A force of 15 newtons is applied to the wrench. So I've drawn a bolt. Yes, you have to draw it. Draw the wrench. It's 15 centimeters long. There's your force acting on it. Now, interestingly, since vectors are free, the arm vector is going off the bolt this way. I'm going to take my force vector and I'm going to move it also off of the bolt and draw the 85 degrees in between. Properties of parallel lines. Do you know this property of parallel lines? Because this is basically what's happening here. I'll draw it actually. I'll really make it visual for you. In the same colors. Oh, I want to do it actually. Make it really obvious. I'm going to draw this one more today. If you have two parallel lines like those two blue ones, do you know the property of parallel lines that whatever this angle is here is always equal to this angle there? That's a property of parallel lines. Interesting, I'm trying to think if that's in any of the curriculums. Properties of parallel lines. I know that it's in essentials, but I don't know if it's in maybe grade 10 or 11. Okay? So the fact that you have 85 degrees here, if I move this vector also on the bolt, that will be the angle between them. So now we have our cross product for torque. You'd have to change the length, 15 centimeters to meters, because your units are Newton meters. Plug in all your values, and then we also always have to, with the cross product, say which direction it's going. Now, right, we're going A, cross, so I'd have to have my hand this way in order to bend my fingers, to have my index finger on A, and my other fingers on F, my thumb would point inwards. And I don't, they can thread a bolt either way. I don't know if you know this, but the most common way is the same way that you twist your toothpaste, right? In this way, if you went from A to F in that direction, and you think about turning your toothpaste cap, it would tighten. And the direction of that vector is inwards. Does it actually make a difference? Like when you're applying torque and you want to tighten a bolt, you want it to go into the object that you're tightening it into? Is that why they just think like you're shooting water down? How do you do that? So you point your index finger to the first vector. So the vector A is your index finger. Now you put your other three fingers on vector V. The only way to do that is to have your thumb pointed inwards to the page.
It's lefty loosey, righty tighty.
Lefty loosey, righty tighty.
Greg says lefty.
Lefty tighty.
Yeah, lefty tighty.
Lefty tighty, right loosey. That rhymes beautifully. You should become a poet. That's a problem with those